Cole here. Welcome back to another video, which I'm entitling, Oh no, I've got a test in like 30 minutes on rotational motion. So let's dive straight into what we're looking at. And so in this video, we're not looking at things like, so we're not looking at like centripetal force, which is mv square over r and that kind of stuff. What we're actually looking at specifically is what we call rotational kinematics. And you can see all these formulas. And if you're looking at this and you say, hey, I already understand all these formulas, and hey, shut the video off. You don't need this stuff. But in case you don't, let's do this. Let's look at a point on this car wheel. And so here's the thing that you have to sit here and think about. The point on this car wheel actually has, we'll say it's got two velocities. It's got one velocity, which is our plain old fashioned velocity. A lot of times when you're doing these problems, they'll call it VT, translational velocity or tangential velocity. Either way you want to call it, the thing is you got to respect about like this car and the wheel itself. It's got horizontal displacement, like we could say that this tire has an X and all that kind of stuff. But here's the other thing. You've also got to look at the point on this wheel, and I know it's a little hard to see here, but I'm trying to pick some colors. But if you think about this tire rotating, think about this tire, and here we'll just let it rotate this much. If you think about this, this tire also has what we call an angular displacement. And so angular displacement, like in this case, if you look over here at this picture, you'd be like, okay, Jason, I got it. Yeah, that wheel has rotated 90 degrees. The thing is, though, we never use the units of degrees when working these problems. So in the case of like 90 degrees, that would be pi over 2 radians. And we always use radians. So every single formula you see on this page, you've got to always make sure that you're in radians. And that's why if you look over here to the side, I think my screen was broke, so I don't know if I can write up there. Hey, nope, that's as close as I can get to writing at the top of the screen. But that's why I started off, though, with these conversion factors that you see up here. And so one of the most common things you'll have to do is always converting back and forth. So say, for example, you had a tire that rotated one complete revolution, a very common thing. We would say the angular displacement of that wheel was 2 pi radians at that point. And now I said a second ago that this wheel has got two velocities. It's got this tangential velocity, like we've always talked about, but you've also got an angular velocity. So an angular velocity, in here, I'll write it again here, omega, and it's measured in radians per second, not square. That was a typo. Stop that. And here's the thing. When we're doing these problems, let's say the car is started at rest. If a car starts from rest, the things that I know is this. I know it has an initial velocity linearly of 0. And then I also know then that means it's going to have an angular velocity initial of 0 as well. And so let's say you're reading the problem and it says the car accelerates to a velocity final of, let's go with maybe 20 meters per second. Well, here's what's cool, and this is why we have these three formulas are so important. Those three equations allow us to go from linear world, and by the way, I've got the letter S here because that's more correct. This distance around the circumference, that distance is what's known. Wow, I forget, I cannot write on the top of my page. But this S, that's what's known as arc length. But here's what's cool. For most problems and tenfold purposes, we can use that in the place of the letter X if we need to. But anyway, these problems, like here is tangential velocity, there's angular velocity, there's linear acceleration, there is angular acceleration. And so if we had a radius of this wheel, then we could then use that to find a final angular velocity. And then, so what is it that unifies everything together? Well, that's time. So if you look down here to the bottom, guys, the thing I want to draw your attention to, and hopefully you notice this, these formulas look a lot like the formulas you've used, especially if you've been learning from me in the past. And here I would usually write x or delta x equals VOT plus 1/2 AT square, and then V square equals VO square plus 2 alpha, not alpha theta, I forgot, we're trying to do linear, right? So this linear, it was 2AX. And so if you notice these formulas, guys, the problems are the same. So like you might work a problem with like a merry-go-round, like this one here with all these kids having such a great, actually I can't tell if they're having a great time or if they're terrified almost, because man, their hair is flying in this. Oh well, AI generated imagery. But here's the thing, like you've got to look at in the problem. This is the easiest thing I can tell you for looking at those problems. If you remember, and let's go back, go way back in time to when I first taught you about linear problems. We would always start them off by looking for 3 of 5 things. And then I would say, hey, I want to ask you a question. And if you remember, the trick to doing linear problems is we needed three. We needed 3 pieces of information in order to work the problem. Guys, here's what's neat about the rotational problems, like a merry-go-round or anything else. It may be going in a circle, but here's what's neat. You're going to have an initial angular velocity, you're going to have a final angular velocity, and then you're going to have, excuse me, not I got to change my letters, alpha, uh, theta, t. You're going to have these things, and guys, once again, what I need you to find are 3 things. And as long as you have 3 pieces of information, hey, Jason, I read the problem though, and it gave me a linear acceleration. Well, cool. If you read the problem, it gives you, let's say it gives you 2 meters per second square. But the problem is asking you like revolutions of a wheel, which again, we can't solve for revolutions. We can solve for radians, and you'll have to convert. Hey guys, that's cool. As long as they gave you like the radius of the wheel, say the wheel had a radius of 1 meter, then all I have to do is use A equals R alpha, and then I can find my alpha. And so likewise, let's say a problem gives you the car travels a distance of 20 meters. All right, cool. Well, I'll use S equals R theta, because if you remember I said a second ago, S and X, basically the same thing for like a car traveling on the road. And then as long as I have the radius, then now I can find this theta. Guys, that's the way basically all these problems work. Now, you might do a problem where it gives you like a 2-part problem. A washing machine starts at rest. Cool. WO equals 0. The washing machine speeds up. Jason, you're drawing a straight line. Yeah, I know. It's just a way of helping make it easier. It reaches a final speed of, let's say, 5 revs per second. Can you do math with that? No, you would have to convert that. So if it gave you like 5 revs per second, you would need to go in there and go, okay, 5 revs per second times, there's 2 pi radians per 1 rev. So you would actually plug 10 pi rads per second in for your final velocity, or 31.4. And then it might give you something and say, then the lid that the machine is open, blah, blah, blah. Guys, if something like that happens, it's just a 2-part problem. And so your final velocity for part 1, that's your initial velocity for part 2. And then you go about your way, and let's say it spins to a stop, and so you end up alpha, theta, t. And I'm pointing this question out because I've seen this one asked repeatedly. And usually it'll ask you, well, how many rotations does it spin through? Solve for your theta in radians for part 1. Solve for your theta in radians for part 2. Add them together, and then you just have to remember that one rotation is 2 pi radians. Guys, that's all there is to this. I know this was a really fast video, but like, these problems are usually not that bad. So as long as you kind of understand the basics, what we've talked about, and all these other equations are just kind of breaking down the idea that angular velocity, it's theta over t, much like linear velocity is just like linear velocity. Linear velocity, if you remember, it's x over t. So, and acceleration, normal acceleration, it's equal to a change in velocity over a change in time. These are just kind of helping you break down what these things kind of represent. Most time you should be good with these formulas down here and these conversions and these things. Guys, you're going to knock it out of the park. I got total faith in you.